In this video, we solve problem 1 of Unit 14. In this problem, we have a proton and an alpha particle. The alpha particle has twice the charge of the proton, so Q sub alpha. We're going to, everything that is related to the alpha particle, we're going to denote by alpha. And this is twice the charge of the proton. So we're going to use the P for the proton. And for the alpha particle, its mass is 4 times the mass of the proton, because it's an helium atom, the alpha particle. Well, they're both moving in a region that has a uniform magnetic field, so they're both suffering the same magnetic field, and each of them is following a circular path with the same radius. So R for the alpha is equal to R for the proton. We're going to just directly say that is R. As they are both circular paths, this means that the magnetic field has to be perpendicular to both the alpha velocity and also the proton velocity. Okay, because they're just circular paths. And what they want us to do is to compare the speed, so the kinetic energy, the angular momentum, about the center of the orbits, and the time it takes each to complete a loop. So this is what we've called the cyclotron period. So let's start with the velocity. So what we are seeking is what is the relation between the velocity of the alpha, the speed of the alpha particle, and the speed of the proton. That's what we are looking for. When the radius is the same. So the simplest way to go here is to remember that with the circular motion, the uniform circular motion that you get here when you have a magnetic field exerting force on a charged particle, it provides a circular path with a radius that is equal to the mass times the speed divided by the charge and the magnetic field. So for the alpha particle, we have that R is equal to m of alpha, v of alpha divided by the charge of alpha times the magnetic field, which is the same for both. And in the case of the proton, this is the mass of the proton, the speed of the proton divided by the charge of the proton and the magnetic field. So if we equal these two expressions, we get that the mass of the alpha particle times the speed of the alpha particle times divided by the charge and the magnetic field has to be equal to the mass of the proton, speed of the proton divided by the charge of the proton and the magnetic field. From here we get rid of the magnetic field and we just solve for V alpha divided by Vp, and this is going to provide the mass of the proton divided by the mass of the alpha particle times the charge of the alpha particle divided by the charge of the proton. This is V alpha divided by Vp is going to be the mass of the particle of the proton divided by the mass of the alpha particle is 1/4. Okay, and the ratio of the charges is 2. The alpha particle has twice the charge of the proton. So this provides that the velocity of alpha is going to be the velocity of the proton divided by 2. Okay. Then after we've done this one, we're going to solve what is the ratio between the kinetic energy of the alpha particle. Okay, and maybe we can just state, yeah, the kinetic energy of the alpha particle divided by the kinetic energy of the proton. So this is the next thing we're going to try to solve. We know that the kinetic energy of the alpha particle is 1/2 the mass of the alpha particle times the square of its speed, and the kinetic energy of the proton is 1/2 mass of the proton, velocity of the proton square. So if we divide these two expressions, we get that the kinetic energy for the alpha particle divided the kinetic energy for the proton is going to be the ratio between the mass of the alpha divided the mass of the proton and the speed of the alpha squared, the speed of the proton squared. So this is This means that the ratio between both is equal to mass of the alpha divided by mass of the proton. This is a 4, and this is 1/4. This is the kinetic energy of both are the same. Both have the same kinetic energy. And then we have to derive the angular momentum. If you remember, we're going to call angular momentum L, okay? And this is what we are looking for. And then here we have to remember that if you have a circular orbit with a radius r and a velocity v, then the angular momentum is r, the cross product between r and p, the linear momentum. This is that the angular momentum is going to be in modulus equal to r times m times v, okay? So for the alpha particle, this is the radius, which is equal to both, and I just name r times m of the alpha times v of the alpha. And for the proton, this is r m proton v proton. So L alpha divided by L proton is equal to the ratio between masses times the ratio between speeds. Okay, so this takes you to the L alpha divided LP has to be, this is 4 and this is 1/2, so this is a 2. Okay, and the last part we have is between the period, the cyclotron periods. So this is T alpha divided by TP. What is this going to be? So to answer this, we have to remember that the cyclotron period is equal to 2 pi times m divided by QB, and this applied to the alpha is 2 pi m alpha divided by Q alpha B, and T proton is 2 pi its mass divided by Q, the charge of the proton divided by B. So if you divide both, you show that the ratio between them has to be equal to the ratio between masses, which is a 4, divided the ratio between the charges, which is a 2. So this is equal to 2.